Chapter 2 concerns itself with matter and the changes in matter and the measurement of matter, and it tries to do so with an application from forensic science. Okay, so changes in the observable matter can either be physical or chemical. A physical change is when the material that you're looking at changes state from solid to liquid to gas. Those are our three states of matter. But the identity of the chemical that you're looking at doesn't change. So it would be available for us to take a cube of ice out of the freezer and allow that ice to melt, and then put the melted water back into the freezer and convert it back into ice, and then take it out and let it melt back to liquid water, and then heat it until it evaporates into steam. In all of those cases, the steam is water, the liquid water is water, and the solid ice is water. The chemical makeup of the material has not changed, but its physical state of matter, solid, liquid, gas, has changed. That's a physical change. In a chemical change, what happens is that the atoms that are stuck together in chemical bonds come apart, and then they rearrange, and then they reform in a new configuration. That's a chemical change. That means that what you start with at the beginning of the day and what you end with at the end of the day are two different chemicals. So if we were to take some carbon that you can find in the lead of your pencil. Pencil lead is actually graphite, it's just a form of carbon. And you burned it, you would make carbon dioxide. What we've done is we've taken pure carbon that is only attached to other carbons, and then taken the oxygen that's out of the atmosphere, and now attached two oxygen atoms to each individual carbon atoms. So the new material involves a new arrangement of atoms. A new chemical has been formed, and the new chemical that is formed as a result of a chemical reaction is called a product. Reactants turn into products. So physical properties and chemical properties are different from one another. A physical property is something that doesn't damage the material that you're looking at. Physical properties can be what we call non-destructive. So melting and boiling occur at specific temperatures. For water, ice melts at 0 degrees Celsius. Water boils at 100 degrees Celsius. Still water. You could still trap that steam, condense it back down to water. You could freeze that water and solidify it back to being ice. Refractive index is a number that we put onto something that if our material allows us to pass light through it, is a measure of how much is that light bent by the material. That's refractive index. And some materials have that, some don't, because some don't allow light to pass through. And then density. Densities are going to be a characteristic material of all matter. If matter is pure, it has a density that somebody has already written down. It's in a textbook, it's on a website somewhere, you can find it. Density is characteristic for pure materials, and it's a number that we're going to come back to and look at a couple of times. Density is mass per volume. So with your eyes closed, if we took two objects that are exactly the same physical dimensions, okay, these two objects are exactly the same physical dimensions. If this one was pure gold and this one was pure iron, with your eyes closed, you would be able to tell them apart because one would be heavier than the other. That the mass per volume is the same for both of these, that the mass per volume would be different. Chemical properties are things like flammability or corrosion. We know that iron rusts. We know that gold doesn't. And how much over time does your material corrode? Flammability. Some things catch on fire very, very easily, and others do not. These are chemical properties because at the end of the day, the rust on the iron is a different chemical composition than it was when it was pure iron. And whatever it is that you burn, you're going to combine with oxygen from the atmosphere, so you're going to make a new product. When it comes to measurements, scientists use the metric system exclusively. So those other units that you might be familiar with, like the pound or the gallon or the pint or the mile, those are not used by scientists at all, because the math that underlies them is just far too complicated for the average person on the street to understand. The metric system, in contrast, is incredibly simple to understand because the math that underlies it is the same every single time. So we're going to have a number of measurements that we call fundamental units. Fundamental units like mass, distance, volume, and time, actually volume's not one, but mass, distance, and time cannot be broken down into something similar, into something smaller. Mass is mass. It's a measure of the amount of atoms, the amount of matter that's in your sample. And mass is measured by the gram. Distance is measured in meters. Time is measured in seconds. Seconds is our unit of time because it is decimal. It can be divided by 10, whereas minutes and hours, those are non-decimal, that there is 24 hours in a day and that there are 60 minutes in an hour. So seconds are our decimal time. Volume belongs to the world of derived units, because a volume is a three-dimensional shape. It is length times a depth times a height. It is a distance times a distance times a distance. It's made up of three other numbers. In the same way that speed is made up of two other numbers. A speed, we would say miles per hour. A scientist would say meters per second. Density, a number that we are going to come back and study soon enough, would be mass per volume, grams per milliliter. Okay, here's how metric numbers break down. Here is the unit itself. So if I were to think about mass, this unit would be a gram. So here we go. I've got 1 gram. If I multiply that up by 1,000, I get a kilogram. And a kilogram is 1,000 grams. If I take my gram and I divide it by 1,000, I get a milligram. A milligram is 1,000th of a gram. If I take my milligram and I divide it by 1,000, I get a microgram, which is 1,000th of a milligram, which was in itself 1,000th of a gram. So a microgram is 1/1,000,000th of a gram. And if I take my microgram and I divide it by 1,000, then I get a nanogram. So a nanogram is 1/1000th the size of a gram. And this works for all of the units. So if I take a second and I divide that second into 1,000 pieces, each one of them is a millisecond. And if I take each of those milliseconds and divide them by 1,000, then each one of those new pieces is a microsecond. And it's true of liters, and it's true of everything. Okay, let's try and figure that out now for, instead of saying kilometers, and using the mile instead. And instead of turning meters into kilometers, we had to do that with inches. We would have to turn inches into feet. So I'd have to multiply them by 12. And then I would have to turn feet into yards. So I'd have to multiply those by 3. And then I would have to turn yards into chains, multiply by 22. And then chains into furlongs, which I believe is 10. And then furlongs into a mile, which I think is 8, but I'm not 100% sure. And so now I had to do all of those individual changes, and I had to know all of those times tables. And yeah, you think you know your 12 times table, but what's 147 times 12? I don't know. But what's 147 times 1,000? There's 147,000. The metric system works in intervals of 1,000, so the answer is always easy. We will only use the metric system in science. We will not use anything that is outside of the metric system. When it comes to measured data, there are two things that we have to take into account. There is precision and accuracy. Precision is a measure of the amount of detail that is in your answer. So for measurements, we'd be looking for answers that have lots of digits in them. If they have lots of digits that have all been measured, then you have high precision. Another way of defining what precision is if you take multiple measurements, is like how in agreement are your answers. Accuracy is something completely different. Even though the word precision and accuracy seem to be used interchangeably in the English language, it's not the same thing at all. Accuracy is how close is your answer to the actual answer. So if you were to ask somebody what time it is, and they said it's 3:15, okay, that's not a particularly precise answer. It might, however, be approximately 3:15 in the afternoon. They didn't tell you whether it was the afternoon or the morning. So you would have to go judge yourself. If, however, somebody told you it is 3:13 and 52 seconds in the PM, they have given you a much more precise answer. They have looked at something that measures time, an accurate watch, and they have given you a degree of precision. They've given you more data. Now, if somebody else tells you, and it's clearly in the middle of the afternoon, somebody else tells you that it is 1:05 and 47 seconds in the AM, well, they've given you a precise answer, but it is wildly inaccurate, because they've given you an answer that tells you that their answer is it's somewhere in the middle of the night, but clearly you can tell that it's in the middle of the day. So precision and accuracy, not the same thing. Precision is in the numbers, and it's going to be measured by something called significant figures. Significant figures are something that I've yet to find a student that actually likes. Everybody hates them, they want to avoid them. It's not that bad. It's not that bad. There is a purpose behind a significant figure. Okay, if I gave a group project where I gave each of 3 people in the class a gold coin and said, go and measure what the mass of that gold coin was. And then we're going to collect the numbers at the end and average them, because it turns out that if you collect multiple answers and then average them, you usually get a better precise answer. And the first person goes over to an analytical balance and measures out that gold coin weighed 1.2403 grams. Okay, that's a very precise answer. It's got 4 digits behind the decimal place. And then the second person went and said that they measured their coin. Oh, and those two are really in agreement. They're a little bit different, but they're in agreement. They only disagree at the 4th decimal place. And then the third person completely misunderstood the task. And instead of using the analytical balance, what they did was they stepped onto a bathroom scale and they measured their own mass. And then they picked up the coin and then they measured the mass of themselves plus the coin. And then they subtracted one number from the other. And they came out with an answer that was just 1 gram. Okay? These 3 people all did the same task. This person did not do that task correctly. They did not have these 4 units of precision right here. These are the significant figures. So now when I ask the students to find the average, the first thing that you do when you find an average is you add those numbers together. Well, what number goes here? If I take these 3 numbers and add them together, what number goes in the 1st decimal place? Now your calculator will tell you that that first number is a 4, and this second number is an 8, and that second number right there, because 3 and 9 is 12, will be a 1, and that will be a 2. But your calculator doesn't understand that one of the people got the question wrong. There is no number here, and therefore you cannot add other numbers to it. This has no precision at all. So when you add these 3 numbers together, the rule of significant figures just calls that number 3. We're not allowed to use these numbers anymore because somebody didn't give you the precision to compare them to. What if that number was a 0.9? What if it was a 0.0? That would radically affect what happens to these numbers when you add them to it. And because we don't know what those numbers are, these are all question marks. You can't include question marks in a calculation. That's all the significant figures is if it's been measured, we can use it. If it hasn't been measured, we cannot use it. We cannot guess what those numbers are because we haven't measured them. Okay? I'll show you a couple of examples of significant figures now. Okay, so let's take a look at how to identify when we're looking at a number on the page, whether that number is significant or not. And the rules are really quite simple, that all numbers, all non-zero numbers are significant. So you count them all, they all count. Zeros, however, are a little ambiguous. Sometimes they are significant and sometimes they are not. Zeros are significant if they are sandwiched between 2 other real numbers. And they are also significant if they are after a number and there is a decimal place, there's a decimal point. Okay, so when I look at the number 1400, 1400, 1 is a real number, 4 is a real number, so I have 2 significant figures already, and then I have a 0, and then I have another 0. So this first 0, is it significant? Well, is it between 2 other real numbers? No, it's not, because the number on its right is a 0, not another real number. So it is not between 2 numbers. Is it after a number? Well, it's after the 4. And is there a decimal point? No. So neither that 0 nor this 0 count as being significant. And this number, 1400, has just two significant figures. Okay? If we divide that 1400 by 100 and make it be 14.00, okay, we've changed the meaning of this number now. That if I were to put something behind this, like grams or seconds, it would tell the reader that those numbers have actually been measured, that we wouldn't just write them in as being zeros if they weren't there for real. So, the 1 is a real number, the 4 is a real number, this 0 is after a number and a decimal point, as is this 0. So 14.00 contains 4 significant figures. It has more detail, it has more precision than just saying 1400. 0.014 has a couple of zeros. We know that the 1 and the 4 are going to count. But what about this 0? Is it behind a real number? No. This 0. That 0 is after the decimal point. And I remember there's a rule about being after the decimal point. But there is no real number in front of it. So neither of those zeros count. And this number has 2 significant figures. 1401, 1401, has 4 digits. That's a real number, that's a real number, that's a real number. So it has at least 3 significant figures. It has a 0. And I look at the rules for zeros, and it says right here, is the 0 between 2 different numbers? Because if it is, then it's significant. And that 0 is between a 4 and a 1. So there you go. This number is precise, and that number is precise, and these 2 numbers are less precise. That's how significant figures work. All right, the rules for using significant figures, there are only 2 usage rules. One is for either multiplying or dividing, and one is for adding. We'll look at those now. Okay, so how we use numbers in a calculation depends on what kind of calculation that is. Significant figures have 2 different rules. One is for multiplying or dividing, and the other one is for adding or subtracting. In the case of multiplying or dividing, our answer is allowed to have the same precision, the same number of significant figures, as the least precise number that was used in the question. So, if I take 1.2403 and I multiply it by 6.11, my calculator tells me that the answer is 7.5782. Now I have to add a little bit of science to what the calculator tells me, because the calculator doesn't know. 1.240, but that 0 is between 2 other numbers, so it counts as being significant. 1, 2, 3, 4, 5. That number has 5 significant figures. This number has 3 significant figures. That tells me that my answer is only allowed to keep 3 significant figures. So my answer needs to cut off here. That these last digits at the end, they're not allowed to count, because I don't have enough precision in my question to allow that amount of precision to be in my answer. And I would allow that 8 to round this 7 kind of messily up to an 8. Okay? When we add and subtract, the rule is ever so slightly different. In this case, the answer is allowed to have the same number of decimal places as the least precise number in the question. Not the number of significant figures, but the number of decimal places. So here, I take 1.1214. Yes, there are 5 significant figures in that number, and there are 3 significant figures in this one. But that's not how I'm going to apply the rule, because this is an addition. I'm going to add those 2 numbers together, and my calculator will tell me that those 2 numbers add up to 39.3214, and then I use a little bit of scientific logic to say this number, the 38.2, only has 1 decimal place. That's the least precise number in my question. That's all I'm allowed to keep. Those numbers don't count. Okay? That's it. That's all you need to know about significant figures. We've known since ancient times that the density of pure materials is characteristic for that material. So the density for gold, AU, is 19.3 grams per milliliter. The density for aluminum, AL, is 2.7 grams per milliliter. And the density of lead, PB, is 11.3 grams per milliliter. So we can use this. Those numbers, they're all printed in the textbook somewhere. If it's a pure material, somebody has already recorded its density. We can use that to analyze whether things are legitimate or not. So here's a question. You've inherited a gold bar. It has dimensions of 10 centimeters by 5 centimeters by 4 centimeters. Notice that each of those numbers has 3 significant figures. And it weighs 3.86 kilograms. Is it pure gold? Or is it a fake? Could it be a lead bar that's just gold plated? Could it be an aluminum bar that is just painted to be a gold color? Or is it really pure gold? Okay, so density is mass divided by volume. Mass is in the question. Volume is also in the question, but it's hiding. So it's a number that we have to work out. Volume, mentioned this a little bit earlier, is a 3-dimensional derived unit. It is a distance times a distance times a distance. It's a length times a depth times a height. So if I take this gold bar that is 10 centimeters long, 5 centimeters wide, and 4 centimeters high, 10 by 5 by 4 is 200 cubic centimeters. Cubic centimeters, cc, is 200 cc. You might have heard of cc's. They're what we print on the side of motorcycle engines. And a cc is equivalent to a milliliter. So 200 cubic centimeters is the same as 200 milliliters. So now my question has a mass and a volume. But when I look at this, I realize that if I take this number, 3.86 kilograms, and divide it by 200 milliliters, then my answer comes out in a different set of units than the units that are being used to determine whether my answer is legitimate or not, because these are in grams per milliliter. So I'm going to perform a little conversion here where I convert kilograms into grams. And I remember from just a little bit earlier that the metric system is always in intervals of 1,000. That there are 1,000 grams in a kilogram. Okay. So the mass that goes here, that's my 3.86 kilograms. And then I'm going to perform a unit conversion that says that 1 kilogram is the same as 1,000 grams. And if I put the kilograms at the bottom here, they will cancel the kilograms that are there. And my answer is now in grams. And then I'm going to divide that by the 200 milliliters. So this is now 3,860 grams divided by 200 milliliters. And the density of my block turns out to be 19.3 grams per milliliter. And when I go and look that value up in the table, it tells me that's pure gold.